Okay, so we've been talking about second-order systems, second-order polynomials, and the polynomials may or may not be meaningful. I want to help show you some tricks or just make sure that we concentrate on how the second-order polynomial can be factored, how we can interpret its meaning, and one of the reasons that we do algebra in engineering is so that we can understand what things mean and how they work. Well, let me show you what I mean, and we'll talk about it as we go along. So, in a math class, you learned something of the effect of a polynomial a s squared plus b s plus c, and we're always interested in finding the roots, setting the right-hand side equal to 0. Now, there's lots of ways of writing this, and some of them may be more meaningful than others. There's also different reasons why we might care about the values of this, why we might do that. So one version of this that I know we talked about was, it ended up being mass times s squared plus a frictional force times s plus a spring constant, and that was equal to 0. And that comes up in mechanical systems a lot. And we've seen things where we had L times s squared, where that was inductance, and there was an R times s, and this variable was 1 over c, capacitance. So we've seen various versions of this thing. In each case, we have interesting coefficients, all three of them. Now, there's different ways you can do things with this. I have this urge whenever I see a formula in this form to divide both sides by the leading coefficient a. So I would get s squared plus b over a times s plus c over a. And I wrote that wrong. B over a times s plus c over a. Of course, if we leave it like that, then it's the same thing. But if I divide through by a on both sides, then it just, since we got 0 on the right-hand side, we don't need it. All right? And so now we ended up with the leading coefficient of this thing equal to 1. And I like that form better, but they're all available to us. You can divide through by these things. One of the things that we want to do to provide meaning is to write this thing as s squared plus omega naught over q times s plus omega naught squared, and that'll be the same thing. And then we can just match up these coefficients, and that'll tell you that omega naught, which we're going to talk about its meaning, but clearly it's equal to c over a by inspection. Then omega naught over q is equal to b over a just by matching these coefficients. Well, this thing implies that omega is equal to the square root of c over a, obviously. And omega is, as we'll see, some kind of a characteristic frequency associated with this system. And if we manipulate this a little bit, we can show that, and I'll just skip the steps because it's easy algebra, that this thing shows that q is equal to the square root of ac divided by b. And we'll come back and talk about q and what it means a little bit more. Because I'm, again, trying to talk about meaning and apply different ways of understanding what these things mean. Now, this is very convenient form for this thing as we go to evaluate things like Bode plots and magnitude responses. When s is real small, corresponding to low frequencies, then this term and this term may be small compared with this term, in which case we can just evaluate for very low frequencies. This whole thing will approximate to omega naught squared. And another form makes it easier to see what happens at high frequencies. So if I divided both sides of this thing by c, I can get another form for this thing, which is a over c out front times s squared. And this will be b over c, s. And now this term can be made equal to 1. So there's different ways of sort of normalizing this. And this form, then, just looking at different ways we can manipulate this thing, I can rewrite this thing into a form. This is really my favorite form. S over omega naught squared plus that same sort of normalized frequency variable, s over omega naught. And now I've divided this thing by q. So this is 1 over q. And in this example, this thing is 1. And that equals 0. And so we can find the roots in these various forms. And again, the definitions that we had here. This one is nice because these are dimensionless quantities in the parentheses. S is a frequency variable but in terms of its dimensionality, and omega naught is a frequency, so they tend to cancel. And so this thing kind of has a a more fundamental character that doesn't depend so much on the problem at hand. And so that's kind of good in some respects. So we'll need a bunch of these things. I don't know, I need to leave myself some room somewhere to work. I'll rewrite these if I need them. So I'm going to start then by just the place that you learned in an algebra class, and I'm going to try and show you some things. I think we've already talked about some of these issues in some of the other videos. The classic way of writing the two roots, this is a second order polynomial, and we know in general it's got two solutions, two roots. And the way you probably learned this is minus b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a, which has got an awful lot of stuff in it. And I'll show you that it is kind of treacherous. It can lead you into a lot of numerical problems in places. If we substitute back in, I think the stuff I just erased, which is all right, we could then, well, one thing that I like to do with this is, let's see what else we can do. Well, we could rewrite this thing. This doesn't make a whole lot of difference, but this thing is b over 2a plus or minus, and then I can avoid having all those fractions in the big thing. I can have b over 2a, that whole quantity squared, minus c. And if you work through it, this is c over a. So this form works, and it's a little bit simpler in some respects. Of course, especially if you can arrange this thing into the form, if you've already divided through by a everywhere, then the remaining coefficient that was out front is just 1. If the thing that was in the leading coefficient is 1, then we can use just minus b over 2 plus or minus the square root of b over 2 squared minus c, which is starting to be a little bit simple. So if you can manipulate the formula in the first place by dividing through by a, then the remaining coefficients are what would have been b over a here. That coefficient goes where this coefficient goes, etc. So maybe we'll do some examples in a few minutes. If I then go back and set these correspondences with the omega and the q form of this thing, this is the way that I think it's worth remembering, and that is that the two roots, S1 and S2, are written as minus omega naught over 2q plus or minus the square root of that same quantity squared minus the c coefficient, which was omega naught, quantity squared. And notice that everything inside the radical here has an omega naught on it, and so that's going to lead us to the form that I think is worth remembering. So this is going to be, and I think we've talked about this before, this is alpha, well, let's just go ahead and write this. We've got omega naught factors out of everything. I get minus 1 over 2q plus or minus the square root of, I didn't leave myself, oh, the omega naught's out front, that's okay. Omega naught times that same thing squared, 1 over 2q squared minus 1. And this is starting to be a little bit simple, and maybe it's easier to go ahead and multiply this guy out, and we get 1 over 4q squared minus 1. That's still a big, pretty complicated equation. I'm going to show you another way. If q is less than a half, then this number, the left-hand side of the left-hand term under here is bigger than 1, so this is a positive number. It's still a big mess. If q is greater than a half, then q squared is large here. This thing will then will be less than 1, and it's easier to write this thing as a complex conjugate form. So this will be minus 1 over 2q here, plus or minus j, and then we're just going to change the sign of this stuff inside the radical, and we get 1 over 4q squared. And this is the form that we used for complex roots. And so we'll come back to this one if we need it. Again, I seem to have left myself not as much room as I would have liked. But all these are good forms, and I'll come back and talk about the things that we want. But I'm going to recommend a different form a lot of these cases. So maybe I'm going to leave all of this stuff right here. And this is the best for real roots. which is q less than a half. And this form is most convenient, hope you can see this, for q greater than a half. All right? So this is the complex form. Now, I'm going to tell you that for the complex form, I think this is about as good as you're going to do. It's as much meaningful as it can be. This one I think we can do a little bit better for when we have real roots. So we'll come to that. Let's make a plot of all of these things as a function of q. So where are these roots? I want to make a plot of the roots of the polynomial, which for whatever it is, in the complex plane. So this is the imaginary part, and this is the real part. And I hope everybody remembers that. It's easy enough to show using this bottom form that the roots of these guys are assuming that the a, b, and c coefficients, or the omega naught and q coefficients, are all positive, then when these are complex conjugate for q greater than a half, the roots are on a circle of radius omega naught. Okay, so omega naught has a meaning, so now we're getting somewhere. Omega naught is the radius of a circle that the roots lay on, in this case where the omega naught and the q are positive. And so the roots would be located here. We can figure out an angle of those roots and the phase. Typically, for a lot of things, these roots are in the left half of the plane, in which case the roots would be written something like alpha plus or minus j times some omega sub I, where this is plus j sub I, this is minus j sub I, omega sub I. Let me make myself some room in here, but this is a circle of radius omega naught. And this is the imaginary parts of the roots. This part is minus alpha, which is the real part of the roots. Okay? And so how does that connect up to the q? Well, it's just written right here. So the alpha term is 1 omega naught over 2q, and this is minus alpha. And then this is plus or minus j, and then omega sub I is omega naught onto 1 minus 1 over 4q squared. So this is the magnitude part. And if you remember in a previous thing, I'm not going to go into this again here, but we'll look at it again later. This part is associated with an oscillatory component, and this part is associated with a decaying part. And we'll see what that means maybe in a little bit more, but we'll be looking at it later. But that is then the form of the sort of natural responses of a system that had our original polynomial as its characteristic equation. So it's really getting us back to the differential equation. Now, another thing to realize is, if we keep omega naught the same and just say, okay, what is q? Well, if q was between a half and infinity, then the roots are on this circle somewhere. So if q goes all the way to infinity, you can easily show that this term goes all the way to omega naught, which is to say the roots would come up here and the alpha, if q goes to infinity, the alpha goes to 0, so it's pure imaginary. So this is where the roots go if q goes to infinity. As q goes the other direction, the roots will go this way for q coming down. So lower q goes this way. All right? So eventually they may be a pair of complex conjugate poles that are just slightly greater than a half, then they'll be here, and eventually they're coming to meet each other. When q goes to a half, this whole thing goes to 0, and the two roots meet each other. That's called the critical damping case, and it's just the case where the two roots become right on top of each other and are equal to each other. After that, it's a little hard to see, but this is what we're going to focus on next. After that, one of the roots gets higher in frequency and one of the roots gets lower in frequency. So one of them goes towards 0 and the other goes to infinity as q approaches 0. And you can see that again. If q approaches 0, well, we're going to talk about that in a few minutes. But this is the situation for complex conjugate roots. It is possible to do the same stuff with q being negative. We'd be over in the right half of this S-plane with pretty much symmetry there. It'll still work just algebraically, just plugging in 0 values of q. And When the magnitude of Q gets to be a half, they'd split on this side as well. But we'll assume that Q is positive for the moment for the purposes of this discussion. Okay, so we've said most of what we can say that's useful about the complex conjugate roots in the S-plane. What happens with the real roots? The issue is that when the Q goes positive, we just end up with this thing. You've got something like minus b plus or minus the square root of b squared minus 4ac, the classic form, over 2a. Even with some simplifications, this thing doesn't really seem to mean much. We've got the difference between some numbers. It's not very good numerically. It's very easy to fool your calculator. I'll show you some examples of how you can get wrong answers from this formula. So let's see if there's a different way of doing this. Here's something that's useful. Let's talk about this. Let's get this thing. We had as squared plus bs plus c. And again, like I say, the first thing I'm just dying to do is divide through by a. So I get this thing into the b over a form, c over a form, like that, which is equivalent to this either of these forms with the appropriate substitutions. But let me show you something here. This is really kind of a big deal. When I see this thing, another thing that I want to do, and I want to train you to do, is say, you know what? Under some circumstances, and we'll work back and figure out what they are, this thing can be approximated as approximately S equals B over A, which is this one divided by that one, times, this is the fun part, I'm going to take C over B. And that's approximately equal to what we just had. And let me show you why, and we'll figure out the conditions under which that's true. Multiply it back out. What is it, the FOIL method? They never taught me that, but I've heard it before. So it's S squared. I'm going to take S, the S coefficients include, there is one from the outside part, which is C over B, and there's another one from the inside part, which is B over A. And then the last one is the product of these guys, which is B over A times C over B, which, let's just make sure we're clear, the B's cancel, and this is C over A is the last coefficient. And now we're on to something. We're getting somewhere with this. So under the condition that C over B, so if C over B right here is much less than B over A, which can happen, and we'll see when in just a second, then we can neglect the C over B term without making a big error. And that's the version I had here. And then this thing is approximately equal to this guy, and that was the form that we had in the first place. So these things are, this is a good factorization if C over B is much less than B over A. If you multiply that out, that says, this is implies that AC is much less than B squared. And if we go back and find my definition for Q, this is the same thing as Q being much less than 1. So Q is equal to the square root of AC over B, and it has to be much less than 1. So for really small values of Q, we can do this approximate factorization. So let me just help you get that. You come up with this thing. You say, look, if the product AC is much less than B, if this term is relatively large compared with the product of the two outside terms, which is all these other things, and we'll have a large Q, then what you should want to do is factor this thing this way. So take this one and come underneath it, under B, and that'll be one of these roots. Take this one and say, well, maybe if we didn't have the A term, we could have S plus B over C equals 0, and this is my factorization. This really gets us somewhere because these things are meaningful. When we put this back into the omega naught and Q form, we're going to be somewhere. This is also something that algebraically maybe is not so complicated, and it'll get us what we want. The other thing I wanted you to notice is, remember that C over A is just omega squared. So let's put some meaning into this. This is a frequency variable. So we've looked at the different roots. This factorization, it's convenient to say let b over a be something we'll call omega 1, and c over b be something we'll call omega 2. Those are both frequencies. Now we have one-to-one correspondences for these. We can figure out what they are. This is really a good thing. Now, these are frequencies. The roots, of course, the root, of course, of these things are, and this is only true to the extent that this and this are equal, which is not perfect, but it's very close. And so what we're going to say here is that the root is at s equals minus omega 1, which was in the left half plane, and the other root is at minus omega 2. And one of them is big and one of them is small. We'd have to think about which is which. All right, now we're getting somewhere. Notice also that the product of omega 1 times omega 2 is equal to c over a. C over a was omega naught squared. Whoops, omega naught, omega sub 0 squared. All right, which is to say the two approximate roots, why I'm having so much trouble writing here, the two approximate roots are equal to, let me try this again, that omega naught is the geometric mean of the two roots. I don't know if you're familiar with the term geometric mean, but this is the definition of it. And so one goes up and one goes down, but their product stays the same. An algebraic mean is the one where one goes up, one goes down, the sum stays the same. This is the product. So this is a little bit different. This is the thing we need. Now, watch this. I can say that omega 1 is approximately, and the approximation is just as good as this, and that is that omega 1 is omega naught times q, and omega 2 is omega naught divided by q. And now we're really getting somewhere. Let me just make sure I got the ones in the way I wanted them. I think I want them to do them the opposite, just do them the other way, just to be consistent with my times 1 over q and times q. So let's see. Q is getting smaller and smaller, so omega 1 is the one that's getting bigger, and omega 2 is the one that's magnitude's getting bigger and the magnitude's getting smaller. Now this is really something because this is nice and simple. It means something. Omega naught is the average of the two frequencies. It's the square root of whatever c over a was. It's a meaningful quantity. Q we're going to talk about some more in just a few minutes. And these are all meaningful things. Now the only thing that's left, and I'm not going to derive this, I'm just going to give it to you, but that is the question, how accurate is this approximation? How good or bad is it? What happens if Q is not sufficiently small? And I'll just write down the actual result if I can find a place to write it. Leave myself a whole lot of room on the board here. I like all these things. I don't want to get rid of them. All right, so here's the actual truth. You can show easily that omega naught, if I can write this right, it'll be easy, times 1 over q. We can write it as some kind of f over q. I'll define f in a minute. And omega 2 is equal to omega naught, and it's the inverse of this function, so it's q over f. The product of these two things is still omega naught, right? So this formula is still done. And f is something that's actually worth knowing. It is given by this formula, which is just this. So f is a function that is 1/2 plus 1/2 1 minus 4q squared. And if q is sufficiently large, f is approximately 1, which is what I said, that these are good approximations. The only question that's left is how close to 1/2 does q have to be before f is significantly far from 1? Well, you can get out your calculator and do it, and here's what you will find. I'll make you a little table. If q is equal to 1/2, that's our worst case scenario, in which case q is 1/2, this thing goes away, this thing is equal to 0, and this thing is equal to 1/2. But if q is, for example, 0.4, you can easily plug this in, 0.4, multiply it out. This number's getting pretty close to 1, and this thing is already up to 80% of its final value. When Q gets down to 0.3, this thing is 0.9, and these are exact. When Q gets to 0.1, I skipped 0.2, but when Q gets to 0.1, this thing is right at 0.99. So let me just reiterate. This f function is negligible, and it's pretty much negligible for Q outside of the range of between 0.5 and 0.3. Outside of that range, down in here, you're only getting a 10% error. And once Q is less than is 10 or more, your error is less than 1%. So for the most part, you just say, I don't know exactly what happens when Q is close to 0.5, but after that, this formula is available to me. And we're going to see that there are many applications where that's just where you wanted to be. And so this having the roots close together means you have to go back and remember this formula. But if you can just live your life in such a way that Q is always at least no more than or is less than 1/10 for all the real roots, then you don't have to remember any fancy formulas. So this is gold. I have to give credit. This came from Professor David Middlebrook, who was a professor at Caltech and one of the great heroes for coming up with all these kind of simplifications. So that's good stuff. So let's talk a little bit more about meaning. This is kind of a logical stopping point, but I'm on a roll, so I think I'll keep talking about it. I just wanted to look at the dimensionality of these things. When we go back to this original formula, this one was for the mass, spring, and damper. The damper is frictional force. And here's the L, R, and C. The resistance form is in here, and we could have solved all these things for the Q. If we do the Q in the RLC form, we would get the omega naught for the RLC thing is 1 over the square root of LC. This Q thing is the square root of LC divided by R. You can just plug into these things with the A's and B's and so forth, and that's what Q means. And in the mass spring damper thing, we had that the omega naught was K, the square root of K over M, or square root of K over M. And when we go to find the Q, we find it's the square root of the product K over M divided by the B coefficient. This B and this B are only coincidentally the same, but it's kind of convenient. Now, let me do something here, and this is good stuff. Remember that the omegas are all in frequency. They're radian frequency. It's radians per second, but it has units of a pure number divided by seconds. So these are all frequencies. And this is called the resonant frequency of any one of these things. In any of these systems, this is the frequency of resonance. What is Q? Q, as we've talked about, has something to do with how fast, if they're complex conjugate poles, roots, how fast does the energy come out of the system? Let's look at this here. These things in the denominator show us the dimensionality of the middle coefficient. In every case, the R is a resistance in this case, where the resistance is the ratio of the force on an electron or something like that to how fast it goes. So R has units of a force divided by a current, where a current is the rate of change of the Q, time rate of change. So it's a force thing divided by a velocity thing. If you figure out, or go back to the original equation for the viscous damping force, it was the ratio of the force, which was all these terms, to the velocity that provided the frictional force. So B is also the ratio. It's an impedance or a resistance, in this case a mechanical resistance, and it's the ratio of the force that you get due to a velocity of the thing that's moving. So these things are actually have things of mechanical impedance or resistive impedance. This thing in the numerator, the square root of AC, has meaning as well, which we haven't talked about. The square root of L over C has dimensions of an impedance, and it's called the characteristic impedance. If you do transmission lines or many other things, it will tell you, well, how big are the impedances in my system? So the Q is then the ratio of the characteristic impedance of the system of R. This thing obviously then is some sort of a mechanical characteristic impedance, the ratio of the square root of the spring constant times M, and B is also an impedance. So all these things are meaningful in ways that we can come back and talk about more as we go along, but it's helpful to have these things that are meaningful. Over here we applied some meaning to the real and imaginary parts of the roots having to do with the complex conjugates. We said that the roots were on a circle of radius, omega naught, so that's meaningful in some sense. We have formulas for it. We said as the Q goes from infinity, where the system has no loss of energy and just whatever energy it had in the beginning, it doesn't ever come out. That would give us Q equals infinity. You can go through the equations. As we decreased Q, with our complex conjugate poles came together. After that, the poles were real. And we said, look, there's this very convenient formula. We had this F function that we can use that is arguably simpler than any of the other forms we used. And it's nice and accurate. But we said eventually we don't even have to worry about that, and we can do an approximate factorization of this thing when Q is small, and we don't have to worry about this F business, which I frequently don't remember. And we just have this, and the fact that as we decrease Q less than a half, that one of these guys goes up and one of them goes down, and their geometric mean their product stays constant. So there's a lot of stuff here. I think you can, if I were you, I would look at this video every semester. Once a semester, I would watch this video and review all this stuff, because otherwise you'll forget it. I don't think there's any fields of engineering where you can't find use for this stuff. And that's why I'm so excited about it. That's why I wanted to make sure you know it. So, don't forget. That's it.